What if one tiny blur of light is enough to shake our entire story of how the universe began? And what if that blur has been traveling toward us for almost the full age of time itself, only to arrive with a message scientists were not ready to hear? Before we go deeper, do this for me. Like this video if you love mind-bending space mysteries, subscribe if you want the universe explained in plain English, and share this with one friend who still looks up at the night sky and wonders what is really out there. Right now, somewhere above your head, there's a patch of sky so small you could hide it behind a grain of sand held at arm's length. In that tiny patch, James Webb detected a galaxy so distant, so early, and so strangely developed that astronomers had to stop and ask a dangerous question. Did the young universe grow up much faster than our best models ever predicted? That question matters more than it sounds, because when scientists talk about the early universe, they are not talking about a vague ancient era. They are talking about the opening moments of everything, the first chapters after the Big Bang, the time when space was still raw, hot, chaotic, and unfinished. According to the picture we have trusted for years, the first stars and galaxies were supposed to appear gradually. Small structures first, dim structures first, messy structures first. The universe was not supposed to be building impressive, bright, chemically mature galaxies so quickly. And yet James Webb keeps looking deeper and keeps finding objects that seem to be in a hurry. This is what makes the story so gripping. It is not just about distance. It is about timing. It is about expectations. And it is about a telescope doing exactly what great science tools are built to do, not simply confirming what we already believe, but forcing us to confront what we may have missed. To understand why this discovery feels so unsettling, we need to slow down and picture what James Webb is actually doing. Webb is not just taking pretty pictures of space. It is acting like a time machine. Light does not travel instantly. It moves fast, unbelievably fast, but not instantly. So when we look far away, we are also looking far back. We do not see distant objects as they are now. We see them as they were when their light first began the journey to us. That means every deep image from Webb is a kind of archaeological dig into cosmic history. Nearby stars are recent history. Distant galaxies are ancient history. And the most extreme galaxies are more than ancient. They are relics from a universe still in its cosmic childhood. Now imagine just how hard that is. As the universe expands, the light crossing it gets stretched. Wavelengths become longer. Visible light gets pulled toward red, then farther into infrared. By the time the oldest light reaches us, it no longer looks like ordinary starlight at all. It has been transformed, stretched, faded, distorted by time and expansion. That is exactly why James Webb had to be built the way it was built. Its giant gold-coated mirror gathers faint light. Its instruments are tuned to infrared. Its mission is not only to see far, it is to see early, very early. So early that when Webb locks onto one of these galaxies, it is not peeking into a mature cosmos filled with familiar structures. It is staring into a universe that is still learning how to become itself. And in that strange newborn era, astronomers expected limits. They expected the first galaxies to be small collections of young stars just beginning to assemble. They expected low complexity, low brightness, very little chemical enrichment. In simple terms, they expected cosmic toddlers. But some of the galaxies Webb is revealing do not look like toddlers. They look weirdly advanced. That is the tension at the heart of this story. One of these ultra-distant galaxies appears to come from a time when the universe was only a few 100 million years old. Think about that carefully. The universe is about 13.8 billion years old. A few 100 million years after the Big Bang is almost the beginning. On a cosmic calendar scaled down to 1 year, that is the first week of January. Not spring, not summer, the first week. And yet this object is not behaving like something from the first week. It appears too bright for its size, too active for its age, too evolved for the stage of history it belongs to. That is why scientists are paying such close attention. If the measurements hold up, then this galaxy is not just another record-breaking dot in the sky. It is evidence that some part of our timeline may be incomplete. Let's make that feel real. Picture the early universe after the Big Bang. First came an unimaginably hot plasma, then expansion, cooling, the formation of simple atoms, mostly hydrogen and helium. After that, the cosmos entered a long, murky period often called the Dark Ages, not because it was evil or dramatic, but because there were no stars yet, no galaxies glowing across space, no cosmic landmarks, just vast clouds of neutral gas spread through darkness. Then gravity began its patient work. Tiny density differences grew, matter clumped, gas fell inward, pressure rose, the first stars ignited. These were probably nothing like the calm yellow sun we know. Many may have been huge, short-lived, and ferociously bright. They lit up their surroundings and began changing the universe itself. Their radiation started breaking apart the thick fog of neutral hydrogen around them. Bubble by bubble, region by region, the cosmos became transparent. Light could travel more freely, structures could emerge. This long transition is one of the great turning points in cosmic history. Astronomers sometimes call it the cosmic dawn. That is the era Webb was built to study. So when Webb sees a galaxy from that dawn period, scientists do not just shrug and move on. Every one of those detections is precious. Every spectrum matters, every photon matters, because each one helps answer a huge question. How did the first simple universe turn into the rich, structured cosmos we see today? But here is where this newly studied galaxy becomes a problem instead of a neat success story. By our standard picture, building a galaxy takes time. You need matter to gather, gas to cool, stars to form. Those stars need to live and die. When stars die, especially in explosive deaths, they enrich the surrounding environment with heavier elements: carbon, oxygen, nitrogen, iron, the raw ingredients for later stars, planets, and eventually life. This process is not instant. It happens in stages. It compounds over generations. That is why astronomers expected the earliest galaxies to be chemically primitive, mostly hydrogen and helium, with only the first hints of heavier elements. That would make sense for a very young cosmos. But some of Webb's distant galaxies are not acting chemically primitive. Their light suggests surprisingly strong signs of heavy element production. In other words, they may have already gone through more stellar processing than expected. That is like walking into a town that should have just been founded yesterday and somehow finding old roads, brick buildings, and a complicated power grid already in place. Something about the pace feels off. And when science feels that kind of mismatch, it pays attention. Now, there's an important point here. This does not mean the Big Bang is wrong. It does not mean all of cosmology is collapsing. It does not mean one telescope found a magical object that breaks physics in half. That is not how real science works. What it means is subtler and more interesting. It means our current models of early galaxy formation may be missing something important. Maybe not everything, but something. Maybe star formation. In the first few 100 million years was much more efficient than we thought. Maybe early gas clouds collapsed faster. Maybe the first stars were more massive on average, which would make them brighter and quicker to enrich their surroundings. Maybe black holes formed earlier and grew faster, injecting huge amounts of energy into young galaxies. Maybe some galaxies had intense bursts of growth that our simulations are not capturing properly. Or maybe the answer is a mix of all of those. That is what makes this discovery so exciting. It is not pointing to one clean answer. It is opening a door to a set of better questions. And the deeper scientists look, the less this seems like a one-off oddball. That may be the biggest twist of all. If this story is expanding your sense of reality, tap the like button now, subscribe for more clear deep space storytelling, and send this video to the one person you know who loves questions bigger than daily life. It helps this channel keep chasing the strangest truths in the universe. Let's talk about brightness for a moment, because brightness is one of the reasons this galaxy is causing so much discussion. In everyday life, bright usually just means easy to see. In astronomy, bright can mean several things. It can mean an object is large. It can mean it is producing stars at a furious rate. It can mean hot. Massive stars are pouring out energy. It can mean an actively feeding black hole is blasting radiation from the core. It can even mean gravity from foreground objects is magnifying the distant source like a cosmic lens. So when scientists say an early galaxy is too bright, they are really saying the underlying engine seems surprisingly powerful for that moment in cosmic history. That forces a chain of follow-up questions. How much mass does it have? How fast is it forming stars? Is there dust? Is there a black hole? Are we seeing a compact starburst region? Are multiple sources blending together? Could some of the light be amplified by gravitational lensing? Could the initial estimate be revised with better data? This is why good astronomers are careful. They do not jump straight from surprise to certainty. They test the signal. They compare instruments. They analyze spectra. They challenge their own assumptions. Real science is not built on hype. It is built on stubborn checking. And that is another reason this story is so fascinating. The drama here is not fake drama. It is disciplined drama, the kind that emerges when nature keeps whispering, "Look again." Now think about the scale of what is happening. A galaxy sends out light when the universe is still in its infancy. That light travels across expanding space for more than 13 billion years. During that time, stars are born and die. Galaxies collide. The Milky Way forms its spiral shape. The Earth forms. Oceans appear. Life crawls, swims, walks, and thinks. Dinosaurs rise and vanish. Humans arrive at the final sliver of the timeline. Civilization appears almost at the last second. Then, one species on one small planet builds a telescope, launches it far from Earth, cools it to extreme temperatures, points it with extraordinary precision, and catches that ancient light. If you pause and feel that properly, it is almost absurd. The discovery is scientific, yes, but it is also emotional. It is a reminder that intelligence can reach backward into time. That curiosity can connect a fragile human mind to events that happened near the beginning of the universe. And what we found when we reached that far was not comfort. It was a puzzle with several layers. The first layer is simple distance. This galaxy is extremely far away, meaning extremely old in terms of look-back time. The second layer is developmental stage. For something so early, it seems unexpectedly intense. The third layer is chemistry. Signs of heavier elements suggest that star birth and death may already have been happening quickly. The fourth layer is statistical context. Webb is not merely finding one impossible-looking object. It is populating the early universe with more substantial objects than many people expected. That combination is what turns an interesting discovery into a serious conversation. So what could the universe be trying to tell us? One possibility is that our simulations of the early universe have been too conservative. Simulations are powerful, but they are not reality. They depend on assumptions about gas cooling, star formation, radiation feedback, and dark matter. If just a few of those ingredients behave differently under primordial conditions, the timeline of galaxy growth could shift. Another possibility is that the very first stars were extreme beyond what we usually picture. These hypothetical first-generation stars are often thought to have formed from pristine hydrogen and helium with almost no heavy elements. Without those heavier elements to help cool the gas, the first stars may have grown very massive. Massive stars burn hot and die fast. That means they could flood their surroundings with ultraviolet light and create heavy elements quickly. A third possibility involves black holes. We know supermassive black holes exist at the centers of many galaxies today, but how did they get so large so early? That question already challenged astronomers long before Webb launched. If black holes could form and grow rapidly in the young universe, they might help explain some of the extreme luminosity we are seeing. A feeding black hole can turn infalling matter into tremendous radiation. In some cases, the central engine can outshine the host galaxy. Then there is dark matter, the invisible scaffolding thought to shape large-scale cosmic structure. Maybe dark matter gathered into early halos in a way that allowed gas to condense and ignite more quickly in certain regions. Maybe the seeds of structure were more efficient than expected at organizing matter into galaxies. And yes, there is always the possibility that some of the earliest headlines oversimplify what later research will refine. Science has a healthy habit of correcting itself. Some galaxy candidates become less extreme after better measurements. Some initial masses or distances get revised. Some dramatic claims shrink when additional data comes in. That caution is not weakness. It is one of science's greatest strengths. But even with that caution, the pattern remains hard to ignore. Webb is not returning a quiet universe. It is returning an ambitious universe, one that seems to have gotten busy early. This is why the phrase rethinking everything resonates so strongly with audiences, even if scientists themselves would say it more carefully. They would not usually mean that literally everything must be discarded. They would mean that one part of our story may need rewriting. And when the universe pushes back, the smartest response is not denial. It is attention. There's also a deeper philosophical reason these discoveries grip people so hard. We like beginnings to feel simple. A child's first drawing is simple. A young city is small. A new language begins with a few sounds. We instinctively imagine the early universe that way too. Primitive, sparse, uncomplicated. But what if the universe became complex faster than we assumed? What if order, structure, and intensity emerged in bursts? What if the first great cosmic systems did not crawl into existence but raced? That possibility changes the emotional texture of the story. Suddenly, the early universe stops feeling like a dim waiting room. It starts feeling like a place of violent creativity, a place where the first stars may have lived hard and died young, where radiation carved tunnels through fog, where gravity built islands of light in the dark, where galaxies started assembling before the cosmic stage even looked ready. And in that version of history, James Webb is not just showing us old things. It is showing us an unexpectedly dramatic childhood of the cosmos. Let's go even deeper, because chemistry may be one of the most important parts of this whole mystery. When astronomers break the light of a galaxy into a spectrum, they can search for fingerprints of different elements. These fingerprints are not random. Each element leaves a distinct pattern. That means distant light can tell us about composition, temperature, motion, and physical conditions in objects unimaginably far away. This is one of the most beautiful powers of science. We cannot travel to those galaxies. We cannot touch them. But we can still learn what they are made of by studying light. If the light suggests more chemical enrichment than expected, then the implication is profound. It means stars had already formed, evolved, and returned processed material back into space quickly. That compresses the timetable. It suggests rapid recycling, rapid birth, rapid death, rapid transformation. And once you compress the timetable in one place, you have to revisit the rest of the picture too. How many first stars were there? How quickly did they form? How fast did small systems merge? How soon did the first black holes appear? How much dust existed? How quickly did galaxies become efficient factories of stars? Those are not side questions. Those are core questions. Here's another way to think about it. Imagine trying to understand the history of a forest. You expect to find saplings first, then young trees, then old growth later, but instead you walk into a zone that should be newly planted and you find thick trunks, layered soil, and signs of regrowth. You would not say, well, trees are fake. You would say, my timeline for this forest is missing something. That is exactly where astronomy may be standing now. We are not watching the collapse of science. We are watching the refinement of science in real time. And that is far more interesting. If you're still with me, leave a comment after this video with the one theory you find most believable. Subscribe so you don't miss the next mystery. And share this with someone who enjoys big ideas that genuinely make the world feel larger. There is also another reason discoveries like this matter beyond astronomy. They shape how we think about our own place in reality. Human life feels large to us because it is our whole experience. History feels long because civilizations rise and fall. But the universe laughs at those scales. A beam of light can spend billions of years crossing space before meeting an eye. And yet, our smallness is not the whole story, because even though we are tiny, we are not irrelevant. A species does not have to be large to be significant. It has to be aware. It has to ask. It has to build tools. It has to care enough to look. James Webb is a monument to that kind of care. It represents cooperation, engineering, patience, mathematics, imagination, and faith that the universe is understandable at least in part. So when Webb finds something strange, that strangeness does not diminish us. In a way, it elevates us. It means we have reached a level where reality can surprise us at the highest scale. We are no longer just staring at stars in wonder. We are interrogating cosmic history itself. That is astonishing. Still, we should stay grounded. Not every anomaly becomes a revolution. Some fade. Some get explained by improved modeling. The brightest galaxies are the easiest to detect, which can distort our first impressions of a population. There may be biases in how surveys are designed. There may be technical subtleties in interpreting infrared data. Caution belongs in the story too. But even after you add all that caution, the central tension remains beautifully intact. The early universe was supposed to be simpler than this. And more than once, James Webb has looked back into that era and found systems that seem to have matured with shocking speed. That is not noise. That is a clue. Whether the explanation is star formation physics or faster structure growth, the frontier is moving. And frontiers are where science becomes most alive. This is why space discoveries capture the imagination so powerfully. They are not only facts, they are confrontations with the unknown. A discovery like this does not just add one more object to a catalog. It changes the emotional atmosphere of the field. It tells scientists and ordinary viewers alike that the map is not finished. There are still blank spaces. There are still sentences in the universe that we have not learned how to read. Think about what the next few years could bring. Webb will continue probing the early cosmos. Follow-up observations will sharpen distances. Other observatories will compare notes. Theoretical models will adapt. Some claims will strengthen. Others will weaken. But the overall result will be progress. A clearer picture, a better timeline, a more honest understanding of how the first galaxies emerged. And maybe that is the real lesson here. Not that our old ideas were foolish, not that the universe is broken, but that reality is richer than the first draft of our understanding. Science is often imagined as a machine for producing certainty. In truth, it is a method for producing better uncertainty, better questions, better tests, better ways of separating what feels right from what nature actually says. That is exactly what James Webb is giving us now. It is not handing us comforting closure. It is handing us sharper mystery. And sharper mystery is one of the most valuable things a telescope can deliver. Because once a real mystery appears, minds move, research moves, technology moves. Entire fields shift around the effort to answer it. Today's confusion becomes tomorrow's paper, next decade's textbook, and one day, a new common truth students will learn. But right now, we're living in the rare middle moment, the moment before the answer hardens. The moment when the evidence is fresh, the implications are open, and the universe still has that electrifying power to make experts look again. And honestly, that may be the best part. Because wonder is strongest not when everything is solved, but when something real refuses to fit. So let's come back to that tiny smear of ancient light. A faint galaxy from near the dawn of time. A signal so old it began traveling long before Earth existed. A message stretched by the expansion of space and rescued by a machine. And inside that message, a challenge to our timelines, to our expectations, to the neatness of our cosmic origin story. Maybe the first galaxies assembled faster than we thought. Maybe the first stars were more extreme than we imagined. Maybe black holes lit up the dark much earlier than expected. Maybe the young universe was not cautious at all. Maybe it was bold, and if that is true, then the opening act of cosmic history was not a slow fade from darkness into structure. It was a rush, a burst, a period of intense creation whose traces are only now becoming visible to us. That idea is thrilling because it means the universe still has the power to surprise us at the deepest level, not just with strange planets or explosions, but with revisions to the very sequence of how everything began. So the next time you hear that James Webb found another faint dot at the edge of the observable universe, remember this. It is never just a dot. It is a chapter, a clue, a time capsule, sometimes even a warning that our assumptions are aging faster than we are. And that is why this discovery matters. Not because it instantly destroys everything scientists know, but because it proves the cosmos is still capable of outgrowing our confidence. It reminds us that knowledge is not a wall we finish building, it is a horizon we keep walking toward. And somewhere beyond the horizon, more ancient light is already on its way. If this journey through cosmic mystery gave you chills, hit like, subscribe, for more scripts that turn science into unforgettable stories. And share this video so more people can feel just how wild the real universe actually is. By the time the next strange signal arrives, our models may already be changing. Our textbooks may already be catching up. Our questions may already be sharper. But tonight, the most honest thing we can say is also the most beautiful. We looked deeper than ever before. And the universe looked back with a surprise.